If we want to model and understand the dynamics of a particle, we can use momentum conservation equation or Newton's second law in this particular form. If there is another system where there are multiple particles, we can still apply the same equation to each and individual particle and solve for it. But let's say if there is a water flowing through a channel, now in this case, in principle, we can still apply the same formulation of Newton's second law or the momentum conservation equation, but the number of particles are humongous. Now it won't be practical if we solve this equation for each molecule, or let's say a cluster of molecules. So there is a alternate possible approach which would be much more efficient, and that approach is the approach of control volume. Now in case of control volume, what happens that we have a fixed space in the region. Okay, now the boundaries can move in this particular case, but we will see it in the future. But the basic thing is that we focus our observation not to a set of particles but to a region of the space, and we see or we track or we model the particles that are coming in through this region and going out. So basically in this particular approach, mass can come in and go out from your system, but in the previous approach, that was the control mass approach, the mass was constant. Now because of the mass coming in and going out, the formulation of the conservation equations will have to be changed, and the exact changes and how those changes would have to be made, we will see it in the future videos. But for now, there are two possible approaches: the control mass approach and control volume approach. The control mass approach is also known as the Lagrangian approach. Control volume approach is also known as the Eulerian approach. So remember the basic thing, that in the control mass approach the mass is constant, and in control volume approach mass is not constant, rather it can come in and can go out. Thank you.